When you strip away the diagrams in textbooks and zoom in on just one piece of light, what does it actually look like? In the energy filament theory, a single bit of light is not a line or a flat wave, but a short, twisted, glowing filament that has already been given a direction and shape, and is being passed forward along a narrow path in the energy sea. From childhood we are shown only two cartoons, a straight arrow called a ray and a neat sine curve called a wave. Both very easy to draw on a board but neither meant to be a literal portrait. In this picture, the universe is filled with a tense energy sea, and matter is made of that sea rolled up into tight loops and structures. Around those loops sits a swirl-like nozzle that we talked about in earlier episodes, a pattern that locks the particles and leaves only certain directions open for energy to escape. When an electron drops from a higher energy state to a lower one, the extra energy has to leave through that swirling nozzle. In that instant, the broad "where could this go" becomes it must go out through this set of openings. So the overall direction of the light is chosen right at the start, not later in flight. Along that chosen direction, the tension and texture of the energy sea happens to be smoother, while the nearby directions are more cramped. So the disturbance is squeezed into something very narrow. You can picture an invisible ring of hoops around the path that keeps pinching the motion into a bright wire. The result is that light is not a fuzzy cloud spreading everywhere. It is more like a very thin, very tight glowing thread aimed along a particular corridor. That thread is not infinite. A single emission is a small packet with a front, a middle and a tail, because the electron does not dump its extra energy in literally zero time. It releases that energy over a tiny time window, and during that window the swirling nozzle itself is slowly turning. Imagine a pasta extruder that is spinning as it pushes dough out. The bit that comes out first points in one direction, the middle points along a slightly rotated direction, and the last bit points along a direction rotated a little more. So the whole noodle comes out twisted. In this view, a photon is like that, while the electron is dumping energy. The swirling nozzle is turning, so the short segment of light it produces is twisted into a helical, rope-like filament rather than a straight stick. It has a definite length in space, set by how long the emission lasts and how fast the pattern is being passed forward. And within that length the head, body and tail of the filament all follow the same basic twist. Once that twisted filament has been formed, the energy sea's job is not to keep spinning it up, but to copy its pattern along the chosen corridor and shove the whole shape forward. Locally, that corridor is almost straight whenever gravity and refraction are weak, which is why the old rule that light travels in straight lines works so well for everyday geometry. The straightness belongs to the path, not to the internal structure. From far away, it looks like a bright streak with some kind of rotating flavor. So we draw a flat wave or an arrow with a squiggle. In this picture we would say more precisely that the twist was built in at emissions, and the energy sea is simply relaying a pre-twisted filament along a nearly straight track. If you could slow everything down and zoom in enough, you would not see a pencil line, and you would not see a flat sheet of waves filling all space. You would see a small, tightly confined thread of brightness whose direction was narrowed by the swirling nozzle, whose thickness was squeezed by the tension corridors in the sea, and whose body was twisted like a tiny glowing rope, being handed from layer to layer of the medium. That is the working shape of light in this view, and it sets the stage for an even stranger question. How can many such twisted threads pass through the same space without shredding each other? Tap follow, share it on New Physics, Clear Universe.